Hi, everyone. Thanks for attending our session on Accelerating Machine Learning with Confidential Computing. Our first speaker today is Antoine Delignat-Lavau. He's a principal researcher at MSR Cambridge, and today he's going to talk about multi-party machine learning with Azure Confidential Computing. Thanks.
Hello and welcome to this session of the Frontiers in Machine Learning session. Today I'm going to talk to you about multi-party machine learning with Azure Confidential Computing. My name is Antoine Delignat-Lavau and I'm a researcher at Microsoft Research Lab in Cambridge, UK. And the work I'm going to present is a joint work between the Confidential Computing team in Microsoft Research, the Azure Confidential Computing team in Azure, and the machine learning team in Azure as well. So in case you don't know, confidential computing is a new product launched by Azure, which is built on technology to help us evolve computing to be protecting the confidentiality of data through its life cycle. So in particular, we want to move from computing in the clear to computing over encrypted data. And this allows us to reduce the trust both in the hardware and software stack and as well as in the Azure operations. So if you're using Azure today, we are already doing encryption for data when it's at rest and when it's in transit. And the new proposition of confidential computing is to maintain data encrypted when it's in use inside the CPU and in the memory. And for that, we are relying on a set of technologies that is called trusted execution environments. So the idea of trusted execution environments is that it's a way to leverage new hardware capabilities provided by CPUs and other computing platforms. And in the case of Intel, the technology is called SGX, and it's a new set of instructions that allows you to set aside private region or enclaves, which contain the code and the data that is going to be protected from the rest of the software stack. And that includes the operating system of your VM, but also the hypervisor and the host OS, and in some cases even protects the code and data from physical access to the hardware. So an important capability that you have, in addition to this isolated enclave, is remote attestation, which is a capability for the hardware to measure and to sign the code and the data that you load into the enclave. And that's important because this is a technology that enables us to build systems where you can be confident that some computation that you do on the cloud is protecting the confidentiality of your data. So what are the benefits of confidential computing? So an obvious benefit is to remove the trust in the platform. So you want to do your data processing on Azure, but you don't want to trust Azure with having access to your data. And confidential computing, it can guarantee that the computation that are performed on the cloud are exactly the one that you authorize and that are measured by remote attestation. It also allows you to reduce the TCB of your application. So instead of exposing your data through all of the software stack, operating system, hypervisor, and host OS, you essentially know exactly the trusted parts of your application that can actually access your data and that will be running inside the enclave. So the other benefits that is more specific to machine learning is to enable new data sharing scenarios. So one example of that is if you want to run a machine learning training of a model, and you want to have multiple participants contribute some data, for instance, some hospitals that want to share patient data to build a diagnostic model. But there is no trust between the entities that are sharing the data. And in addition, you also have no trust in the platform that will be running the computation as well. And this is possible, again, because of remote attestation. So you can only encrypt the data that you will contribute to a key that will be known to the secure enclave. And this guarantees that nobody else, including the cloud operator, can actually have access to the data, and that it is going to be only used to perform the authorized computation. So as an example of that, we have built a scenario where we can actually do diagnosis of COVID-19 from chest X-ray pictures. And for that, we are combining two data sets. So one of them is a COVID-19 case database from the University of Montreal. And the other is an unrelated data set, which is about pneumonia detection, which has been published by the Radiological Society of North America. And the idea is that we want to combine these two data sets to create a machine learning model. So in this case, we are going to use a ResNet model, which is a standard for image recognition, and is going to provide better accuracy and enable diagnosis based on submitted pictures. So if you want to do a machine learning training operation like this today on Azure, you would typically express it using what is called the machine learning pipeline. So a pipeline, it represents the flow of data through a set of computations or computation operations. So in this particular scenario, we have two input data sets which we want to pre-process and to aggregate before we feed them to the ResNet model, which we are just going to take from TensorFlow. And if you were to expose this on Azure ML today, you can actually create these kind of pipelines using this editor or designer, where you can actually drag and drop some nodes which perform operations like executing some Python scripts or loading some datasets, and you can execute them on Azure. And the way that Azure ML will actually execute these pipelines is internally the nodes in the pipelines in the graph actually represent containers that perform some data processing operation. So in the case of, for instance, executing a Python script, you will have a container that will take the Python script, mount the associated datasets, and write the output to some folder. So when Azure ML is actually executing these pipelines, what it does is that it creates container images that is going to load on container registry, and it's going to deploy these containers on your training compute. And Azure ML supports a wide range of training computes, but in our case, we are interested in executing pipelines on confidential computing virtual machines. So we are going to use SEC VMs to actually deploy the containers. So another thing is that, as I was saying before, secure enclaves typically are used to execute a small reduced TCP version. But in our case, what we actually want to do is we want to execute arbitrary Python scripts. And for that, we depend on the ability to execute a machine learning framework like TensorFlow or PyTorch. And for that, we need a lot of support for the Python runtime, which is why instead of trying to carve out a version that we can run from the enclave, what we actually do instead is that we are going to provide operating system-like functionality in order to actually execute the full runtime and the complete framework. And it's a trade-off essentially between TCP size and code complexity. So at the cost of increasing the TCP, we get the ability to actually execute unmodified framework like TensorFlow. And for that, we rely on the Linux kernel library, which we execute on top of OpenEnclave SDK. And it provides a well-defined interface to the host for operations like memory management, managing mounted file systems, networking, and signals. So when we want to actually execute these kind of containers inside enclaves, So the way it works is that we are going to encrypt every file system that is used, and that includes the root file system, which contains the code of the framework and all of the dependencies, as well as all of the disk images that actually contain data files. And these disk encryption operations are done using the Linux device mapper, where we use dmcrypt and dmverity for disk encryption and disk integrity. And in addition, we implement a key management system to actually automate management of disk encryption keys using Azure Key Management Service. And we also implement new protocols to export keys from the key management service into the LKL image. And that's a process that must be performed without having to trust Microsoft services. And for that, we rely on remote attestation. So in order to export a key from the key manager to the LKL enclave, we need to actually present a valid quote or an attestation coming from the enclave to the key manager, and it's going to wrap the key using the LKL wrapping key to actually perform the export. So going back to our scenario of COVID-19 diagnosis, the way that we write the pipeline is that every node in the pipeline becomes a node that is going to perform execution of encrypted container, and we are going to have every input represents an encrypted file system that we mount inside this container runtime. So in this case, we are going to have 2 containers for preprocessing, 1 container for aggregation, and 1 container for actual training. So if we look at the full picture of execution of confidential pipelines, the idea is that we have 2 stages. So the first stage is an agreement stage, where we have all of the parties that are going to contribute code and data to the training computation or to the pipeline. They have to come together to create an agreement over the shape of the computation, and this is reflected in a file that is called a pipeline manifest. So this file is going to describe all of the containers that will be used, encrypted in the pipeline, and as well as all of the input datasets, which are going to be encrypted by every data contributing party. So after this agreement stage, we are going to move to the execution stage. And before execution, every data contributing party must encrypt their datasets and upload their dataset encrypted to Azure Storage. And they must also install the encryption key for their datasets to the key management service with a key export policy that is going to authorize execution on the pipeline manifest that has been agreed. So in this model, we assume that every participant has their own subscription and can independently manage their keys and their encrypted datasets, but one of the parties is going to be hosting the computation, so they also need to have a provisioned SEC virtual machine to actually perform the computation, and this will be used by the Azure subscription that executes machine learning pipelines to deploy the confidential container image and perform the mounting of encrypted file systems and the exports of keys from every participant. So at the end of this process, we execute every node in the pipeline, and the output of execution is an encrypted file system as well, whose encryption key is also installed on the key management service. And importantly, the encryption key for this output file systems has a key export policy that only authorizes the next stage in the pipeline. So, of course, there is also the final stage, which contains the train model. And for this one, the idea is that we want to be able to deploy the train model on a confidential inference service. And For that, we also have a design where we port the Onyx runtime to OpenEnclave, and we can manage the encryption key for the inference service to actually query for inference the encrypted model without ever revealing the encryption key of the model to any party. So it's also possible to do other configurations. So you may want to release the encryption key for the train model of your pipeline to a subset of the data contributing parties, or you may want to only authorize the use of the train model through confidential inference, in which case the actual model is never available to any participant. So this concludes my presentation on the confidential multi-party training, and I will now move on to an actual demo where I show you how it looks like in practice when we want to train a COVID-19 diagnostic model.
To simplify the demo, we are going to put all of our scripts in a single container for the preprocessing, aggregation, and training steps. The first preprocessing script is for the COVID-19 dataset from the University of Montreal. For preprocessing, we will decode, resample, and label each picture using this metadata file containing the information about the patient, the name of the radiology picture, and the diagnostics such as bacterial pneumonia, SARS, or COVID-19. Some of the data has inconsistent labels, so we are going to normalize to 3 labels, one for normal, one for pneumonia, and one for COVID. So then we are going to read the datasets, and for every image, we are going to decode, standardize, and resize. And this gives us the first preprocessed dataset. The second dataset is the one from the Radiological Society of North America. And it also comes with a metadata file, which has the name of the picture and a label. And this dataset only contains normal and pneumonia labels, which is why we need to aggregate with the other datasets for COVID. Finally, we have the training script itself, which is a simple wrapper around the function to invoke the model, and just as extra arguments to set the inputs and output folders to the proper mounting points for the disk images. Here we have the Docker file that contains all of the script, and it needs to contain all of the dependencies, including TensorFlow and all of the Python packages that we use in the preprocessing script. Next, we need to build the Docker container, which normally takes a while, but here we have most of the operations already cached. And when this is done, we need to encrypt and upload the container to storage. Normally, encrypting the full container and uploading it takes a few minutes, so I'm going to skip ahead to show you that here we have computed the root hash of the container, and this can be used in the pipeline manifest, which is shown here. The main part of the manifest includes the definition of the container images that are used, and as you can see, we only have one, which is the one that we just created. The declaration of the encrypted disk images, so you can see the 2 images corresponding to the input datasets, as well as additional images that corresponds to the intermediate outputs of every node. And we need that to know what size to allocate when we create the output disk images. Next, I'm going to encrypt and upload the first dataset. And for that, you only need to provide the folder that contains the data. And the script is going to create the encrypted disk image, compute the root hash, and upload the image to storage. Finally, it's going to install the encryption key for the image on the key manager enclave. Similarly, we are going to do the same operation for the second dataset. It's going to create the disk image, encrypt it, upload it to storage, and install the encryption key to the key manager service. And because this is a larger dataset, I'm going to skip ahead. As you can see, this takes a few minutes to complete. Okay, now that we have encrypted and uploaded both the container and the disk images, we are actually ready to execute the pipeline. So I'm going to call this Python script that is going to turn the manifest into an actual AML pipeline definition. And here you can see that it's submitting the pipeline to AML. So we get a link to the Azure Machine Learning portal, which essentially allows us to track the execution on the Azure ML portal. In this case, you can see that every node in the pipeline has finished executing, which is indicated by the green check mark. And we can go ahead and click on one of these nodes to look at the outputs that have been collected by the execution engine. Some of these outputs have been generated by the management code of AML, while others are coming from the LKL launcher, including the configuration of LKL that you can see here. We show that we are calling the first preprocessing script and the disk configuration. We also have the output of LKL itself, because LKL is attaching console outputs of the enclave to the host, and we can use that to actually look at the outputs of the preprocessing script itself. This is the command line that we use to submit an inference request. So in this case, we have 5 sample patients that we want to run against the model. And for that, we first need to create an encrypted and attested secure channel between the client and the inference service. So here you see that we obtained a quote by the enclave that confirms that the key has been produced by the inference service. And we are going to submit the inference request and get back the prediction. So here you can see for each patient what is the probability for each label.
Thank you for the presentation. I'm happy to take questions.
Hi, my name's Alex Seamus. I'm from Microsoft Research Cambridge, and I'll be leading the Q&A. I just want to say thank you, Antoine, for your great session. So I'm going to ask the questions from the audience. Does this enclave protect GPU-bound jobs?
Yes, so that's a great question. So as the name implies, confidential computing is based on special hardware capabilities. And if you want to execute on GPUs, then we actually need specific features on the GPU or whatever hardware accelerator that we want to execute on. Because if we run on this kind of training jobs on existing NVIDIA GPUs, you have just many ways to access GPU memory and to actually read the training data during execution. So current GPUs do not protect against active adversaries, and they don't have the same guarantees. So fortunately, we have one of the next talks from Emmett that is going to give some more details.
Great, thank you so much. So the next question from Emmett is, are there any side channels that are part of your threat model?
Right, so people know in that field, side channel is pretty much one of their top concerns, especially when we are executing on CPUs, because CPUs, they are essentially executing code that is coming from different parties, especially when we are in a cloud setting. So if you execute your training on a VM that may be also shared by other tenants, then there is a risk that some of the shared hardware features, like shared caches, can be used to try to extract some of your data. So in general, I think our long-term vision to mitigate these side channels is we want to actually execute confidential training jobs in environments that have limited shared resources, because that's kind of the most efficient way to restrict these side channels. As for current mitigation, well, we have a lot of software-based mitigations, a lot of compilation strategies to actually flush caches and limit sharing as much as possible. But of course, they come with a performance cost. So it's always a difficult balance to find.
Thank you. So Tristan Ewan asks, is this enclave dependent on the presence of specific hardware? For example, Intel SGX, and is it limited for use on other types of CPUs?
Yes. So as it stands, we need to have these specific CPU features to actually protect the enclave and to perform attestation. What we have designed with Azure Confidential Computing is a system that is as agnostic as possible as to all of the specific details of the hardware implementation. So in particular, our key management services, our attestation services, we design them in such a way that you can use them for different hardware implementation of trusted execution environments. And that's basically one of our important goals in designing these services is, yes, we require specific hardware features, but we try to abstract them at the platform level.
And can you talk a little bit about the availability of these types of CPUs? Is it just SGX? What other type of TEs are available?
Yes. So today you have several implementations available. So Intel has been leading that space for a while with SGX. On the AMD side, so AMD is working on a technology called SEV, and that's providing you with similar guarantees, but in a slightly different model. So you can use it for essentially running full VMs encrypted rather than just small enclaves. There is also trust zone-based technologies coming from ARM, and they have new iterations that are also in the pipeline. And then, of course, you have all of the implementation in accelerators. And that's a kind of active research field in the industry.
Thank you. And can you tell me a little bit about what's the performance overhead of training my model within an enclave? Do I have any limitations that I would need to worry about?
Yes. So we try to make the experience as flawless as possible. And that's the value proposition of using this container technology is we want to be able to execute arbitrary Python training script as if you were running them locally. In practice, we have to we have some limitations that are coming from hardware, from the details of the hardware implementation of trusted execution environments. So, for instance, in the current generation of Intel SGX, we have a limited size for the enclave memory, which is called the EPC. And what that means is if you're using more memory than this limit, which in current Azure VMs you can get is about 256 megabytes, then the Intel driver is going to swap page using software encryption, and that's going to be a very big performance hit during training. So at this stage, with current Intel SGX, you have kind of a significant limitation in the number of parameters you can use in your model. What's coming next is Ice Lake is getting deployed in Azure pretty soon, and that will lift a lot of the memory limitation that exists today. And what we are left with is overheads that are coming from data encryption. And in most cases, these overhead are not very significant. So certainly, it's you are losing a few percent for this overhead, but it's pretty close to the performance you have just training natively.
Great, thank you. And for one final question, how does the confidential computing compare to other privacy-enhancing technologies such as homeomorphic encryption and multi-party computation?
Yes, so that's a great question, and at Microsoft we are actually interested in all of these technologies, and we have research teams that are working on all of them. So at a high level, the main value of hardware security-based confidential computing is that you have the smallest performance cost, and certainly the performance cost for homomorphic encryption and multi-party computation has been going down by order of magnitude in the past few years. But there is still quite a big gap, and I believe that Raluca is going to give some more details during her talk.
Great, thank you so much. So now I'd like to introduce Raluca Adapopa, who's going to give her talk.
So hello everyone, my name is Raluca Adapopa and I'm a computer security professor at UC Berkeley. Today I'm going to tell you about our work on a secure collaborative learning platform. Organizations often need to learn from data across different organizations, but they often also cannot share it because it's sensitive. Let me give you an example from anti-money laundering efforts. Banks want to detect money laundering, but criminals often hide their traces across different banks. If a bank wants to detect money laundering and looks only at its own data, they won't be able to detect money launderers very effectively. But if they can look over the data of multiple banks, they can detect them much easier. Therefore, banks would like to learn from data across different banks. However, they cannot share their transaction data with each other because they are in business competition. This is a quote I like from the Chief Risk Officer of Scotiabank. He says that in the future, collaboration will be vital via analytics and advanced encryption mechanisms, which will enhance yields in terms of finding these attacks of money laundering by orders of magnitude. Besides this financial use case, there's many other use cases also in the medical sector or in even nuclear facility auditing or in cloud-based video analytics. That's why my students and I have been developing our MC² platform for secure collaborative learning. MC² stands for multi-party collaboration and competition. And the philosophy is that an organization should be able to share its data, but without showing it. MC² is an open source effort that I'm leading in the RISE lab. So within MC², we're taking two separate approaches. One is using secure multi-party computation, or MPC, and the other is using hardware enclaves such as Intel SGX, for which there's, for example, Azure Confidential Computing provides a cloud. Let me tell you a little bit about MPC at a high level because we'll need it later in the talk. So in MPC, there are end parties that have sensitive data that they're not willing to share with each other. MPC enables them to compute a function over their data and learn the result of that function, but without sharing data with each other in the process. Essentially, what happens is that the parties exchange encrypted data and compute on the encrypted data to obtain an encrypted result, and then jointly decrypt that result alone, but in the process learn nothing else about the other party's data. The reason we are using either an MPC approach or a hardware enclave approach in MC² is that there's a trade-off between these two approaches. Different use cases prefers one over the other, and there's no winner. So MPC has the downsides that it is slow and expensive for complex computation or big data, and it requires a compute cluster at each organization. Hardware enclaves don't have these downsides, but instead they require trusted hardware, which brings assumptions and brings the required hardware setup, and it also suffers from side channels. My students and I have contributed in both of these directions, and our projects aim to reduce the downsides of these approaches. For example, for MPC, our projects are designed to provide efficient protocols for various tasks. For example, Delphi does CNN inference, Helen does linear model training, Bost et al. Does classical ML inference, and then we have a set of more recent works that try to design automatically efficient MPC. On the hardware enclave side, our work has been to eliminate a large class of side channels through Oblivious computation. For example, our work on Visor provides CNN inference inside hardware enclaves using Oblivious computation. So I don't have the chance to tell you about all of these different works in this talk. So instead, I'm going to focus on one of them in particular, namely Helen. So Helen is joint work with my student Wenting Zhang, who deserves the credit for this work, as well as with my colleagues Joey Gonzalez and Jon Stoik at UC Berkeley. Helen provides a maliciously secure MPC for collaboratively training regularized linear models. And by maliciously secure, what I mean is that P minus 1 out of P parties could be malicious, could even collude with each other, but the remaining part is still protected. So if you engage in such a collaborative computation, you only need to trust yourself with the confidentiality of your data. So to clarify the scope of Helen, in Helen we assume that the parties choose their inputs and that the final result, the model that was trained, is shared with all the parties. There is a separate direction and complementary direction of work that tries to prevent against parties providing poisoned inputs or tries to provide privacy mechanisms so that the model doesn't reveal a lot about the data it was trained on, such as a differential privacy. But these are complementary to Helen, and Helen focuses on the efficient MPC for the training so that you don't share data in the training process. All right, so there's been a bunch of prior work trying to develop efficient schemes for training linear models. However, they are not maliciously secure, and many of them focus on only two parties. The one class of protocols that actually are maliciously secure are generic MPC. But generic MPC is slow, it's expensive. For example, if you take a generic MPC platform such as Speeds and you train Lasso using it, and using SGD, stochastic gradient descent, running in Speeds for a reasonable data set, it takes at least 3 months to train a model. So this is not efficient. Instead, with Helen, we're able to reduce this 3 months to less than 3 hours for the same level of security and accuracy. So the reason is that Helen is a synergy between systems, machine learning, and cryptographic design. And let me give you a sense of how Helen works at a high level. So in Helen, we are considering a small number of organizations, let's say around 10. And each organization has a lot of data. So N, the number of records, is much larger than the dimension, namely the number of different fields of each record. So here is why, if you just take SGD and run it for inside an existing generic platform, here's why it's slow. With SGD, you take a chunk of the data at a time and you run a generic MPC protocol that's quite expensive across the parties. But then you repeat this for every chunk of the data, so essentially you end up running the MPC a number of times that depends in N the large number of records. And that's very, very slow. To be able to make the cryptographic computation efficient, we really need to make sure that the MPC computation does not depend in N. So our first insight is to develop a specialized protocol, cryptographic computation, that scales independently of the number of records, but of course maintain functionality and security. So the first technique is to provide an alternative formulation of the problem that makes cryptographic computation more scalable. And by alternative formulation, I mean a reformulation of both the algorithm and the data. So when it comes to reformulating the training algorithm, we have realized that the algorithm ADMM, which stands for Alternating Direction Method of Multipliers, is an existing training algorithm, but it is much more fit for cryptographic computation than SGD. The reason is that with ADMM, the parties scan their data and produce a short summary that does not depend on n. And then with this summary, they have to run a much smaller number of iterations using generic MPC. So this is better for MPC because you run the MPC on a summary, which does not depend on the number of records. And also you run this MPC fewer times because you have fewer iterations with ADMM because you are scanning the data initially. And ADMM is well studied and has very good accuracy. So this is great. However, this is not enough. And the reason is that we are considering a malicious setting where parties could misbehave arbitrarily, and in particular, they might not compute their summaries correctly. This is particularly a concern because a wrong summary could correspond to there could be no actual inputs data that could have led to that summary. And for example, a summary could bias the final result much more than any one party's data could. Okay, so we really need to make sure that the parties are providing a summary for which there exists an original valid input data set. Now, the parties are allowed to choose that original input data set, but there must exist such input data set that led to the summary computation. So another possibility to address this problem could be to use zero-knowledge proofs. So at a high level, these proofs enable a party to prove that they computed the summary correctly. But at the same time, it's in zero-knowledge, so they're not revealing their data. The problem with this is that they are also expensive cryptographic computations. So now again, the expensive cryptography depends on n, the number of records. So again, things are going to be slow. Instead, here is where we're going to use our alternative formulation of the input data. So the insight is to try to find a smaller input that preserves the summary. And for that input, there should exist an original, legitimate n by d input that led to the same summary. So we realized that actually singular value decomposition of the inputs, of the input data of a party can provide such a summary for us. Using singular value decomposition, we're showing in the paper how we can actually, the parties can input a much smaller data set, d by d, and for any such small data set, there exists an original, big, legitimate n by d data set. But at the same time, this smaller data set preserves the summary. So what this means is that now we can use a zero-knowledge proof to prove that the summary was computed correctly from one of these reformulated smaller inputs. And this zero-knowledge proof right now does not depend on n, but depends only on d, which is much more efficient. So basically, here's we are at this point. We have this generic MPC that runs between the parties. It runs for fewer iterations because of our choice of ADMM. It runs on the summaries because of our choice of ADMM. And we can have zero-knowledge proofs to check that the summaries are correct. And these zero-knowledge proofs also only depend on d by d, the number of dimensions, and not on the n, which is big. Actually, in the paper, we have another technique that reduces this generic MPC to a much simpler and more efficient computation, but I will leave that for the paper. All right, so this was a gist of how Helen works. So let's see a little bit of evaluation for Helen. So we evaluate here Helen on 4 parties, on different regions, on EC2, and we compare it to running SGD, which is the go-to algorithm for training a linear model, and we're comparing to running SGD inside a state-of-the-art MPC platform speeds. So we are evaluating it on the song prediction dataset of 90 features, and here the x-axis shows the number of records per party, and the y-axis shows the time. It's all exponential axis, and here's some helpful indicators for the time. So with the baseline, so with the existing framework for MPC, the time to train depends on the number of records. But with Helen, it doesn't. So it does actually depend on number of records, the plain text local computation, but the cryptographic computation through our techniques does not depend on the number of records. And that's the expensive one. That's why the line for Helen looks flat. And overall, for only 100,000 records, Helen is already 900 times faster. So this was Helen, one example for training linear models in a maliciously secure setting. But besides this, we have all this other work on tackling different aspects of machine learning in a collaborative sense, in a collaborative and privacy-preserving sense. So these projects are part of our MC² open source effort, which already has a few examples of adoption. So for example, IBM uses one part of MC², Opaque, for their Rest Assured medical project. Ericsson has been using a part of MC², namely training XGBoost models in a secure collaborative way for telecom data. And Financial and Alibaba have also used this piece of MC², and they have also contributed to it. And we have a collaboration with Microsoft, Azure Confidential Computing, and with Scotiabank for the anti-money laundering use case I mentioned above, and we already had 2 successful POCs with them. So in conclusion, I told you about MC², which is a secure collaborative learning platform. It's open source, and it embodies the principle of sharing without showing the data. Thank you.
So thanks, Raluca, for this great talk and the summary of the work that your group is doing. So I think we can start with a few questions. So the first one is there any accuracy performance trade-off using the summaries as opposed to using the original data as you described in the Helen work?
Thank you for having me, and thank you for the questions. So that's a great question. There isn't any trade-off for Helen, and that's because the summary preserves correctly the input for the purpose of the training. Again, for this specific linear training algorithm, this wouldn't be the case for other training algorithms, but for this specific training algorithm of linear models, the summary preserves the accuracy completely. Security-wise, it's also preserved because we add the zero-knowledge proofs to prove that the summary was computed correctly. And it just really boosts performance a lot because the slow secure computation no longer depends on all the records in the database, which are many, but only on the summary. So overall, it's a win.
I see. And speaking of zero knowledge proofs, so I guess the performance overhead. So what is the performance overhead? Because there is another question that says, try to understand what are the performance overheads coming from, but also trying to understand how you reduce these 3 months of training down to 3 hours. So if you could shed more light on basically how your optimizations improve the training time, but also what are the existing overheads that maybe it's worth looking at and try to overcome in future work.
Right. Very good question. So I would say that what our techniques are doing is they're reducing the performance overhead from 3 months for training the same model. I mentioned the parameters of the data set size in the talk from 3 months to 3 hours. So that's a significant improvement in performance for the same security guarantees as compared to using state-of-the-art tools. Now, you're asking a great question, what is left in those 3 hours, especially since to actually train this model using regular data, no cryptography, it takes just a few minutes. So there's clearly a significant increase there in performance overhead. So I would say the zero-knowledge proofs take a lot of the time of those 3 hours. So if you are in a setting where you don't worry about a malicious attacker, but only an attacker, so-called semi-honest. Basically, a semi-honest attacker is one that can look at the data of a party, but is not going to actively change what protocol the party is running. So if you can trust the parties to not actively change the protocol, but just to be curious and look at the data, then with semi-honest security, I would say you can take it down to probably half an hour or less, even less. And what's left in that half an hour? Well, there's still a bunch of cryptography going on. There's still an overhead of blowing the data a little bit up by converting it to cryptographic shares. There's still a bunch of network communication. So that's kind of hitting the barrier of how good MPC platforms that we have today are.
Right. And I think there's a follow-up question, the accuracy performance trade-off. So the audience is asking whether, does it mean that the summary contains all the information? So given that you can tolerate reducing the input data just down to a summary.
Yeah, so I see this question from Zio Williams. That's a really good question, Zio, and I completely agree. Where is that? Well, it sounds a little bit counterintuitive here because you have a ton of data. How can you summarize in a short amount of data? So actually, what's interesting is that the training algorithm itself doesn't takes the data times the data transpose. So basically, what happens is that the input to the training algorithm already is not the whole data. The training algorithm, all that it needs for this linear model scenario in particular, all that it needs is the data times its transpose, which already is a summary version. So no, the summary is not retaining all the data about the original data, but it's retaining everything that the training algorithm would receive as input, anyways. So that's why there's no loss in accuracy for the training process, but indeed the summary is much smaller and is not actually containing all the data because actually the training algorithm doesn't take all the data essentially as input.
Right. And I guess the next question is actually I was trying to ask the question, but the audience is already asking this. So they're asking why the approach was limited to linear models. So I guess the question, generic question would be, how is it to generalize this approach to cover other machine learning algorithms and other models that are not subject to the linear models that you described in the talk?
Yeah, very, very good question, Peter. Thank you for the question. So we have 3 techniques in Helen, and not all of them would apply for something like logistic regression, which is more complex than linear regression. So, for example, but some do apply. So, for example, the ADMM algorithm, the alternating direction method of multipliers, actually applies to logistic regression as well. So you can use it to improve cryptographic training of logistic regression as well. However, the local computation step with logistic regression would not be linear anymore. So then we can't use our second technique in the talk about how I didn't talk a lot in this specific talk about it, but in the paper about how we actually make the local computation, if it's linear, much more efficient. There's special cryptographic tools for linear computation that are fast. But if you try to apply this approach to logistic regression, the the local step would no longer be linear, so you couldn't apply that specific technique, and it would be much, much slower to handle a nonlinear computation. So basically, some techniques apply to logistic regression and beyond the linear models, and some don't apply. But overall, we don't really have as efficient of a logistic training algorithm right now that's maliciously secure. So that would be very interesting future work, and it would require some other technique as well. Great question.
Right. And I think there is also a heated discussion about Enclaves versus MPC. And I think there are two interesting there are two interesting questions. And I think for the interest of time, I'll try to ask one question that tries to cover all of them. So hardware enclaves can deliver better performance than MPC. That's my understanding. Yes. But at the same time, MPC can give you a better threat model, like lower TCB and so forth. Now, I think the question is, I guess, space. So I would like to get your thoughts on whether there is any room for trying to get ideas from that you explore in the PC and bring them to Enclaves and try to get, let's say, the performance overheads of MPC lower while not sacrificing much of your security and vice versa. So any thoughts on that?
Yeah, great question. So it's a very natural question to think, okay, how would I combine MPC and SGX? So there are some ways in which you could re-up some of the benefits of both, but I fear that you would also suffer from downsides of both. So for example, one, I think an interesting idea is to put MPC inside SGX, but because of the integrity guarantees of SGX, you may only need to use semi-honest MPC. So maybe you don't need to use malicious MPC, you don't need the zero knowledge proofs, because maybe SGX can prove, using remote attestation, that it has done the computation correctly. So then you think, okay, great, I'm going to remove the zero knowledge overhead of MPC. But a bunch of downsides still remain. There's still attacks and side channels on SGX that subvert remote attestation. So they would affect the integrity. There's also attacks that if an attacker could do them to every SGX machine, they could put all the MPC data together. So then they reconstruct the whole data, because in MPC, you need at least one party who wasn't compromised. So there's still some of the side channels issues of SGX that remain. And there's still the downside of semi-honest MPC is not that fast. It's not as fast as raw execution inside Enclaves. So I feel that indeed, by putting them together, you would get some of the benefits of both, but also some of the downsides of the both. So it's yet another trade-off. And at least so far, I haven't seen something that would mostly re-up the benefits. That's a very interesting question to think about. And now the other thing I do want to say is that there are common things, common problems to both. So there are common problems that have to be solved for both, such as how do you make sure that the data a party puts in the computation is not, poison? Or how about what you release from the MPC or from the enclave? How do you provide some privacy for guarantees for what that leaks? And for example, differential privacy is, one possible tool. So basically, there's still commonalities of problems between these two different approaches.
Awesome. Yeah. So thanks, Raluca, for the great talk and the very interesting Q&A. So now we have to move to the final talk in this session, and the next speaker is Emmett Wichel, who is a professor at University of Texas at Austin, and he's going to tell us how to do secure computing with cloud GPUs. Hope you enjoy the talk.
Hi, my name is Emmett Wichel. I'm from the University of Texas at Austin. I'm here to talk to you today about secure cloud computing with GPUs. This is work that was done in my lab at the University of Texas at Austin with some of my graduate students and my collaborator, Chris Rossbach at UT, and who's also at VMware Research. So there recently in the news have been some very high profile security vulnerabilities that have been disclosed for computer architecture. Talking about Meltdown, Inspector, you've probably heard of. These are very troubling security vulnerabilities because they take isolation boundaries that we previously thought were impermeable, things like the user kernel boundary and the boundary between processes, and it shows that in fact attackers can move through these boundaries. So what do I mean by this? We have over here sort of a picture of an attacker and a victim, and the attacker is going to execute some legal but maybe strange code. In this case, execute a bunch of branches, which is going to put the hardware, which is a shared resource, in a particular state. And in that state, when the victim executes their code, whether it's executing it normally or in some cases even speculative execution, it's going to create some effect where the data inside the victim is actually written into this hardware state, which is then read by the attacker using time. So in the example of Meltdown, what you actually had was the attacker would set up the victim to do a speculative load. That speculative load would get squashed, but the data would still make its way into the cache. And then the attacker could determine using timing that that data was in the cache. While the high profile vulnerabilities have been in the architecture, there have been timing and side channel vulnerabilities that have been disclosed in the operating system and in GPUs. And what unites all of these is this idea that an attacker can reach into a victim's address space and steal the data within that address space. And that's something that we didn't previously think was possible, but now we find out it is. And unfortunately, completely fixing these isolation boundaries is probably going to injure performance. And so we're looking at a world where we enter a bunch of mitigations. So this is a very unfortunate situation. One of my graduate students, Tyler Hunt, thought it was similar to the movie They Live. If you've seen that, the protagonist in that movie gets a pair of sunglasses, which allows him to see that rich people are actually disgusting aliens who are subjugating the rest of us. And just as in that movie, these attacks are allowing us to see that these isolation boundaries that we previously thought were sort of great examples where we had created an impermeable barrier are in fact quite porous. So one of the big themes of this talk is going to be that communication timing leaks your input data. And that's because the timing is proportional to the amount of work you're doing. And you communicate all the time. You communicate every time you go across a machine in between CPUs, and you actually communicate also across devices between the CPU and the GPU. And when you're executing things like training a neural network, executing algorithms like training a neural network, that involves a lot of communication. There's some technologies that are intended to increase the security of your computation. Things like Intel SGX and ARM Trust Zone, if you've heard of those. But using these technologies still requires a lot of care. They don't solve all of our security problems. We sort of wish that we could sprinkle this sort of security pixie dust on our systems and have our systems become secure. But part of the message of this work is that it still actually takes care to build a secure system, even using these improved pieces. And finally, how much should your average AI researcher or practitioner care about this problem? That's a question I can't really answer. The purpose of this talk is to simply give you an idea of what these problems actually are and what it takes to build systems to fix them. So in order to really dig into this problem, let's take a look at a specific example. And in this case, we have a person who has some sensitive input, some input that they want to keep secret from their cloud provider, who in this case is Google, and we'll see why in a minute. And the sensitive input goes into the cloud platform, and they're just going to do machine learning inference and return some recognition results. So what are the problems that I might have in terms of using this service? Well, I might be afraid that Google uses a lot of complex software, and that complex software might have bugs. And if it has bugs, then attackers can exploit those bugs and steal my data. And that's why I use Google, because maybe Microsoft doesn't have any bugs. But there are other problems. Like, for instance, the cloud provider might have their own interests and their own motivations. For instance, they might want to monetize user data. Or you might have a situation like 23andMe gets acquired by GlaxoSmithKline, and suddenly all of your genetic data is being used to design drugs. Maybe you think that's fine, maybe you don't. Finally, while a platform cloud provider has a certain business incentive to be a good actor and to safeguard my data, there are administrators that are employed by the platform that have access to the privileged software on the machine. And these administrators might have their own motivations. And in fact, if you want to read some stories about malicious cloud platform administrators, just Google it or send it to Bing. So we don't have a lot of basis for trusting our cloud provider, but unfortunately, trying to get rid of that trust is difficult. And the reason it's difficult is the obvious reason, and that is the cloud provider is in control of the operating system and the hypervisor on these platforms, which means they have access to all of our computation secrets. They have access to the address space on the CPU. They have access potentially to the address space on the GPU. They can see all the communication channels and all the data on the platform. And again, just to be clear, it's the privileged software on the cloud, in this case, that is the threat. That's what we're concerned about, because we're assuming that this code is coming from us or is coming from some trusted source, but we want to execute it on an untrusted platform. And in that case, it's the privileged software that can spy on us. So how are we going to get trustworthy cloud computation, that's where TEEs come in. TEEs, or Trusted Execution Environments, are a technology that is intended to help in this situation. In particular, it provides a hardware root of trust that is independent from the software provider. So what I mean by that is that as a remote user, I can be assured that my code is running as I compiled it and on a legitimate piece of hardware for, let's say, Intel's SGX. That means I don't have to trust the software on that system to know that my code is executing as I compiled it. That's very valuable. Also, ARM has a version of this called Trust Zone. It's not quite as powerful, but it's along these lines. So TEEs give us this technology that allows us to not trust the privileged software on the cloud provider. But even there, we're going to see that we have to be very careful how we use TEEs, that they in themselves, the technology in itself, does not sort of mean that any system we build with it is then secure. Now, I've talked to you a bunch about trusted execution environments on the CPU. These are viable technologies which are out in the marketplace and you can purchase them today. The work that we've done also relies on the idea of there being a trusted execution environment on your GPU. So that does not exist commercially, but there are research proposals, including the excellent Graviton by Stavros that was published in OSDI 2018. There have been some other proposals, and what unites these proposals and makes them realistic is that all the performance critical hardware on the GPU remains unchanged, but you sort of add some security features and you can potentially achieve a trusted execution environment on a GPU. So if we had such a thing, how would we use it? I'm going to describe to you the system we call Telekin, and it uses a client CPU and a cloud GPU in order to do secure computing. Now, the client CPU we're assuming is trusted because you have physical control over that machine. You bought it, you physically administer it, you've installed all the software on it. And then we want to use just the cloud GPU. So in this case, your application does not need to be modified. Even if your home computer, or maybe this is an on-prem computer in, say, a hospital, doesn't have to have a GPU, but it was compiled with the idea that it did have a GPU, and anytime it makes one of those GPU calls, that local call is turned into an RPC, a remote procedure call, to the cloud. And that RPC then schedules some computation that runs on the cloud GPU. Every API call gets turned into an RPC, which executes on the remote machine. In fact, there's also on the CPU in the cloud, there's a GPU API proxy that has to be there for technical reasons, but that piece of software is not trusted. Everything is encrypted end to end from the source CPU to the trusted execution environment on the GPU in the cloud. So this is an attractive organization to build our system, but unfortunately, as it is, this is still insecure. Why is this design insecure? Because while the computation occurs within the trusted execution environment, which provides this hardware root of trust, unfortunately, there's still a lot of communication which is visible to attackers. Attackers looking at the PCI bus, that's like the operating system or the hypervisor in the cloud machine. Attackers looking at incoming network traffic, even attackers out in the network see this communication and can do timing attacks on it. Okay, so for the rest of this talk, we want to answer these three questions. The first is, can information be extracted from our GPU communication patterns? And not surprisingly, the answer is going to be yes. I'm going to demonstrate to you a communication timing attack. Then we're going to ask, how can our system remove that information? And the answer is we're going to replace GPU streams, which is how a CPU normally communicates with a GPU, with something we call a data oblivious stream. And the data oblivious part means that the communication with the GPU is going to be completely independent of your input data. And that's going to break the causal link and make it impossible to leak information about your input data. And finally, what's the performance cost of all of this stuff? It's actually surprisingly reasonable. It's about 20% for neural network training. The caveat here is you have to execute a lot on the GPU. So there's increased communication latency that we introduce, but as long as you spend most of your time executing on the GPU, your overall end-to-end runtime stays relatively constant. And I probably won't get too far into the execution time breakdowns. Okay, so let's take a look at the timing attacks that we were talking about before. So let's just break down what's going on here. We have your standard picture of a deep neural net that has several different layers. And the thing that you have to know when you do inference on these things using a GPU is that each layer of the neural net is evaluated by one or more GPU kernels. And it's the kernel launch and completion interrupts, which maybe your attacker is witnessing on this PCI bus, that gives you execution timing on the GPU. So we don't attack the GPU directly, but we see by communication with the GPU how long it takes these kernels to run. We count the kernel executions, which are deterministic, and that lets us know what layer in the neural net we're executing. And the question that we have is, what can the operating system or the hypervisor learn about the input images from the execution time of these layers and of these GPU kernels? So in order to figure this out, we measured a ResNet, a DNN, on several image classes from ImageNet. In this case, it's sharks and dogs, and these bars represent mean, runtime, and the error. And you can see that in this case, the runtime is between these two classes is indistinguishable. But in these cases, there's a small runtime difference, but it is statistically significant. And we can use that information to figure out what was in the input without actually seeing the input. So here's the attack. So we have an application. This application takes an input image, it classifies it using a deep neural network, and the output is the image class. Now, our attack does not see a single pixel of the input image. What the attack sees is the timing of the neural net that's doing the inference. Just by looking at the timing, as shown by this communication pattern with the GPU, we build a classifier that outputs the image class. So we're not seeing the image, but we are still classifying what was in the image. And the question is, how well can we do with this attack? And here we have random guessing, which, for two classes, random guessing is obviously 50%, 33%, 25%, blah, blah, blah. And you can see with our classifier, so with our using machine learning to attack a machine learning inference system, we can get almost 80% accuracy for two classes. And in fact, we're 60% better than guessing all the way down to 8 classes. And in fact, this there's a long tail on this distribution. We're better out to about 30 classes. So that's concerning. So there is a communication timing attack that happens even if you're using sort of the latest and greatest security technology. So how are we going to remove this threat? That's what I'm going to talk to you next about replacing GPU streams with these data oblivious streams. So let's look at some more detail about what I'm talking about when I say the CPU is communicating with the GPU. So here I've actually broken it down into what actually goes on when you do one of these inferences. The first thing that happens is there's some sort of memory copy where you're taking the input image and you're copying it over to the GPU. Then you're launching a series of kernels. These kernels represent the computation that's being done as part of the neural network inference. As you run each of these kernels, there's a message to start the kernel, and there's a message that the kernel is completed. And then finally, we generate some recognition results, and those are copied back to the user. So as you can see, timing information is abundant in this situation. The mem copy has a particular timing. The launch kernel has a start time. It has an end time. The final mem copy also has timing information associated with it. Operations are distinguishable through other side channels, through other sort of incidental features of the computation, things like what kind of hardware do they use. Some of these computations, like the mem copy, use the DMA engine. Some of them don't, like the kernel launches. There are other potential side channels, like the commands may be different sizes, and the application API pattern might depend on the secret input data. So if this bit is a 0, make 2 of these calls, and if this bit is a 1, make 3 of these other calls. So what we have to do is eliminate this timing information that is present in the communication with the GPU. And we do that by transforming the GPU stream into what we call a data oblivious stream. We do this using a client-side library called libTelekin, and all of these application calls remain unchanged, but they get intercepted by our library, which then puts them on a queue and is going to use fixed rate communication with the GPU. So whereas previously we had this stream, so we have mem copies and we have kernel launches, because those are the 2 types of operations. And so we do schedule them independently, getting to some of the details here because that's good for performance. We are going to split and pad the commands as necessary to enforce a uniform size. And here we're going to see these blobs, which are different sizes and they're happening at different times. When we transform them, now suddenly you can't tell them apart. And so in order to make this happen, we have to add padding, we have to add no-op kernel launches. Those are fairly easy to do and fairly easy to disregard on the GPU. But the thing that we do have to do is we have to say, we are going to schedule our operations on a fixed schedule, fixed with respect to time. So we're going to launch 32 kernels every 15 milliseconds. We're going to mem copy 1 megabyte in both directions every 30 milliseconds. We are going to use a fixed amount of bandwidth, regardless of the performance requirements of our underlying application. So that's the cost. As far as the actual execution time overheads, they're only about 20% for neural network training. I'm basically run out of time, so I'm not actually going to go through these performance overheads in any detail. I will skip through this, but basically the idea is we are using a fixed amount of bandwidth and we can achieve low overheads because the GPUs are busy and their computation overlaps with all the extra work that we've inserted. Sorry, so here's the breakdown of the overheads, but not going to go. I'm just going to flash it by really quickly. And I'm just going to conclude by saying the talk has presented secure computing with cloud GPUs, and we achieve this security by eliminating the communication timing channel that happens between the client CPU and the cloud GPU. We do that with data oblivious streams. This is transparent to applications because we maintain GPU API semantics. And what I mean by that is if you mem copy a kernel and then execute it, the GPU knows to wait for the mem copy to complete before it does the execution. We preserve that. And if you do this, the whole system has modest performance overheads for the level of security provided, which is quite high. Thanks very much.
Thank you so much, Emma, for this fascinating talk. Really appreciate that you could talk to us a little bit about training GPUs, using GPUs to train securely inside of a data center. Have a couple of questions for you, and if anyone wants to chime in on the chat, we'll be happy to ask Emma these questions too. But to just kick off, you predominantly spoke about GPUs, and as we've seen, there's a proliferation of other accelerators. Can you talk about how your work would work with different types of accelerators?
Sure, yeah. So thanks very much for having me and giving me this opportunity to talk about my work, the work of my students. So accelerators, in general, it's sort of tempting to batch them up, and yet I think the challenges are sort of dependent on the exact nature of the accelerator. So for instance, for tensor processing, it's not clear, first of all, it's not clear exactly what they're doing because a lot of that hardware work is not sort of open source. And then it's not clear exactly what the threat model should be because we don't know what the operating system and the hypervisor sees as far as the tensor processing unit. So for an example of something that we do know, as far as the encryption facilities on your processor, that's no problem. You know, when you get context switched, the operating system can wipe out all that state and keep strong isolation between different contexts. So that's not a problem. Whereas a GPU is sort of like a sort of a persistent state machine. It's got like thousands and thousands of registers, and it's got a lot of in-flight computation. And so you can't just wipe out that state and not have it affect performance. And so GPUs are sort of a particularly interesting case for how to make accelerators secure.
Great, thank you. And we also have a question just to follow up on the security of GPUs from Don Bevier saying, do the regularly spaced requests still leak info to a power attack?
Yeah, let me just be clear that as far as our threat model is sort of public data center. And I'm actually not so worried about somebody hooking up a power meter to a machine in a public data center. From what I understand, they have very strong physical security, and I'm really concerned about software attacks in the data center because those are able to be launched by attackers and administrators. That said, as far as power goes, I haven't really thought it through. But certainly fixed rating is a good first step toward trying to keep power constant. But I would have to think a little bit more and think about what the operating system can do in terms of ratcheting power down. And I don't really know, but it's not in our threat model, I think, for good reason.
Have you considered other type of side channel attacks directly on the GPU from a host OS versus a guest OS where most users will be running? So this is again protecting more against the cloud operator rather than somebody else using the cloud.
So from the guest, I'll tell you. So I'll tell you sort of one of my philosophies about sort of trying to make GPUs secure against side channels, and that is I'm not a big fan of sharing them. Because if you're running if you have two different tenants that are trying to share the same GPU, that seems like a really hard problem because there's a very complicated memory system with certain limitations and bandwidth and a lot of fancy hardware scheduling. And I feel like that's there's published attacks for one tenant attacking another. And the truth is that virtualizing GPUs is such a challenge that their utilization is generally low. And so having that be the cost to make a GPU secure seems acceptable to me. And without the changes to the GPU hardware, I don't see how you're going to get multi-tenant security. We could ask Stavros because there was stuff in Graviton about multi-tenant security, but I think there's some gotchas down that road.
Well, let me then take you in the opposite direction of, have you looked at what would happen with your model when you use multiple GPUs and try to scale out to a data center scenario? Yeah,
so let me say that we actually have multi-GPU experiments in the paper. So we do support multiple GPUs. The sort of caveat is that all communication has to happen back through the client, which for certain workloads, that's perfectly fine, but that actually introduces communication latency, but it's perfectly safe and you can absolutely scale out. The thing that we didn't look at that people use is when you have direct GPU to GPU communication via something like NVLink. In that case, we would have to fix rate that communication. And we took a look at that and it seems possible, but it was beyond our engineering budget for the project.
Great, thank you. And then to ask a couple more questions from the audience. So Stephanie's asking, what are your recommendations for future GPU API semantics to reduce overhead on performance of TEs?
So that's a very good question. I guess sort of philosophy-wise, I've made a research career out of backwards compatibility. So I tend to take certain things as given. That's why in the first talk when they were using the Linux kernel library, it certainly makes sense to me because the amount of engineering effort that goes into TensorFlow is very, very high, and so trying to get a custom version of that doesn't require certain kernel facilities seems difficult. And so, if the actual GPU API is fairly stylized, and we don't have too big a problem transforming it into this form that is data independent. I guess the one thing I would say is there are idioms that the programmer can use, and the more asynchronous you are, the better our system can be in terms of hiding latency. And I didn't get into performance, but at the end of the day, not surprisingly, if you execute a lot on the GPU, we don't harm your execution time too much. And if you don't execute a lot of time on the GPU and spend a lot of time communicating, well, we put a wide area network between your CPU and your GPU, so it's going to slow you down.
Great, thank you. And then, so we have time for one final question, and again from the audience. So Peter writes, asks, I found it interesting that the timing between differences between sharks and dogs was only evident on the first 2 layers of the neural network. Do you know what caused this? I would have thought that the number of operations in all layers should be data independent.
Yeah, so look, first of all, I really appreciate this question because this really surprised us. Okay, this was not something, we did not go into this project thinking like, oh, we're going to nail these inference systems. We actually figured like, well, that's probably not going to work, but whatever, we'll just sort of build the system anyway, or try to build it, based on some threat model that we thought was reasonable. And what I showed you in that case was a total simplification, right? Because just to have it fit on a slide, there's actually hundreds of layers, hundreds of kernels, and almost 100 layers. And the timing of some of the layers is data dependent, and the timing of other layers is not. And I will say, we spent a lot of time trying to understand what was making the layers sort of what signal were we picking up on? We were picking up on in a lot of cases, the number of zeros that were happening because those floating point operations are faster. But that showed up both in processing the raw pixels and also in the convolutional layers internally. And maybe it was, I don't have a lot of super machine learning expertise, and maybe with more machine learning expertise, we could sort of drill down to figure out exactly what layers were doing this data dependent computation and sort of how to display it. I really wanted to have sort of the picture that shows it's the circular feature detector, or it's this convolutional layer that does it. And the signal was sort of spread out across several layers. And so it was hard for us to figure out what the underlying regularities were that we were pulling out of there.
Thank you for that, and thank you to all our speakers, to Emmett, Antoine, and Raluca for coming and talking to us. We've got a half-hour break now, and we'll continue at 11 a.m. Pacific Standard Time on the security and machine learning session. Thank you very much, everyone.
Thank you.